Swayam Prabha. Digital India. Educated India.
Welcome. In the last class, we have been discussing the Rouse model to discuss the motion of a polymer chain, and we have started deriving the equation. First, we wrote in discrete terms, then we wrote a continuous version of it that is true for large number of segments. And today, we will go on solving the equation into what we know as the Rouse modes. So, just to recap, the model we have been trying to build is the continuous analog of the bead spring model, where we have a contour variable n going from 0 to n, and the position at any point is given as r as a function of n and t, and at that point we are having a random force Fr as a function of n and t. If I divide by zeta, I call it random velocity Vr. So this was the Rouse model, and the equation was for r and t, we are solving a partial differential equation where we have the boundary conditions at the two ends, that the gradients of r vanish at n equal to 0 and n. So, what we have is a partial differential equation, and it is of course difficult to solve when we compare that to an ordinary differential equation. So, the method we adopt is we try to write this partial differential equation into a set of ordinary differential equations which are easier to solve, and then I refer to the solution of those one dimensional the ordinary differential equations that we get as the Rouse modes, and using that we can get the solution of the Rouse model. So, the goal here is to write equations in the form of ordinary differential equations like this, because we know how to solve these equations, and this is what we have got for the Brownian motion of a free particle, just like one sphere in a solvent. And to do that, of course, you cannot work with just one ODE, because the PDE is a higher dimensional equation. You will have a series of ordinary differential equation that represents that. So, this equation that I have written is for p equal to 0, 1, 2 and so on. Okay. So, what I do is known as a linear transformation where the variable I have defined, the xp, which is now a function of t alone, is given as the integration over r and t multiplied by a function phi p n that I would refer to as a basis function, and so far I am not saying what the basis function is, but the basis function must satisfy this particular relation for xpt, where xp is a solution of the equation I have just written. Let us call that star. Okay. So, now let us look at the equation that we have written on the previous slide. So, now I have constants zeta p, that is a drag coefficient, but it is changing for different values of p. So, we will assign a meaning to it in a moment. Similarly, we have Kp analogous of a spring constant, but defined for an ODE for a value of p, and similarly Fp is like a random force that is defined for a value of p, and of course, that is changing as I change the values of p. We do not know what the values are yet, we will derive the values that would give any meaning to this equation. Okay. So, now since we have defined xp as integral over n of phi p n multiplied by r and t, if I plug that in the equation above, what we have is the left hand side is the following. Of course, I can move the time integration inside the integral, because the integral is over n, not time, and phi is assumed to be not a function of time, it is only a function of p and n. So, we can write this as we have to be slightly careful here, because outside its total derivative d by dt, when it is moved inside, then since r is a function of both n and t, I have moved to partial derivative dou by dou t. But this we already know from the original equation, this is equal to the term we have on the right hand side. So, I will plug that in there. So, this becomes k by zeta dou 2 r by dou n square plus f r t by zeta. So, now this is equal to that is the first term, and this is the second term. So, we will first do the integration by part over the first term, and then we worry about the second term here. So, let us look at the first term, which contains an integral like this. Of course, it has some prefactors, we will worry about that later. So, we use the integration by parts and the rule is, if we have a product of two functions integrated over the variable x, this is equal to f of x integral of g of x dx minus integral of f prime of x gx dx integral of dx. So, this is the rule I am going to use here, where I set f of x is equal to phi of p n and g of x as my second derivative of r with respect to n. So, now, and of course, x in our case is n. So, now this is equal to phi p n, and we integrate f of x, that is my dou 2 r by dou n square. So, if I integrate the second derivative, I will get the first derivative. From 0 to n minus integral of dou phi by dou x. Again, the integral of second derivative is the first derivative, that is n here. So, we have dou r by dou n dn. Now, the first term goes off because dou r by dou n is equal to 0 at n equal to 0 and n, that is the boundary condition. The second term, I will use the integration by parts again, where this now becomes my f of x and this now becomes my g of x. Let us call it f1 and g1, and this is my x. When I do it again, I will get and then we have plus like that. Okay, so once we have derived the equation for one term there, so I want to put it back into the expression that I had earlier, that is right here. So, I have zeta p dxp by dt is equal to, we can take zeta p by zeta common and take it outside, and inside we have two integrations. For the first integration, we have showed what to do by parts. Second integration is as it is. So, the first integration becomes integral from 0 to n k phi p n dou 2 r by dou n square dn, and the second term here is as it is. So, zeta p by zeta is taken constant. So, we have 0 to n Fr and T phi Pn, and then we have Dn right here as we had in this expression. Now, I want to replace this term right here with what we have derived, that is right here. So, we have this equal to zeta p by zeta into minus k multiplied by dou phi Pn by dou Nr, and this goes from 0 to n, and the second term is right here plus k dou 2 phi Pn by dou n square r integrated from 0 to n. That is what we have gotten right here, and then the last term remains unchanged. This entire thing is equal to minus Kp Xp plus Fp. This was the original equation we started with. Zeta p dxp by dt is equal to minus Kp Xp plus Fp. Xp by definition is 0 to n dn phi Pn r, and Fp I write as it is. Now, there can be many possible solutions to this particular equation. We will look at a particular solution, because any of these solution that satisfies the ordinary differential equation that I have just written will suffice for us. It need not be a unique solution, it can be any solution, because we are transforming the variable to get a linear ODE, and there may not be a unique solution. There can be multiple ways to linearize the PDE that we have. So, one possible way is we look at the term by term in the two expressions I have written. So, first of all, I look at the last term in the two expressions by green here, and I will equate these two terms, and what I do get is Fp is equal to zeta p by zeta 0 to n dn phi Pn Fr of Nt. That is my first equation. Now, I look at the other term here. So, this term right here has to equate to the two terms right here. So, in that the first term I will set it to 0 by assuming that dou phi Pn by dou n is equal to 0 at n equal to 0 and n. This will set the first term here, that is highlighted in green and yellow, to be equal to 0. Now, we have the second term remaining, that is equal to the term right here. So, the second term is then equal to the following. Okay. So, this is one way of getting a solution for what we have written, and again I want to emphasize that this is not a unique solution. There may be other ways of solving it, but this one will suffice because this already transformed the PDE to the ODE we want. We need not care about a unique solution. We can get any solution that will work because any transformation is will work for us. Okay. So, if I look at this equation, I can also write as something like this. So, now you can see we have a partial differential equation in terms of the basis function that I am trying to solve for, and we know the boundary condition that basis function also satisfies. So, using that we will solve for the basis function, and using that basis function I can define the solution xpt. This is what we are going to do. So, let us get started. So, we have an equation of the form because all the constants that we have are assumed to be positive. That is an assumption again, where a square is my kp by k divided by zeta p by zeta. The general solution of this will be phi p n is equal to alpha cos a n plus beta sin a n, where alpha and beta are arbitrary constants. You can verify this by doing the first derivative, that will be this, and then the second derivative, which of course is equal to minus a square phi p n. Okay. So, if I look at this general solution now, and if I now use the first boundary condition, at n equal to 0, we can put n equal to 0 here. The sin term is anyway 0. The cos term will give me beta a is equal to 0. You can see a equal to 0 will be a trivial solution because this will give me the kp values to be 0. So, we go for beta equal to 0, then I will use the second condition at n equal to capital N. Beta is already gone. We have from here alpha a sin a n is equal to 0. Of course, a is not equal to 0 because it is a trivial solution. Alpha, if we set equal to 0, again we get a trivial solution. So, alpha equal to 0 is trivial. So, we set sin a n equal to 0, which gives me a n is equal to some, sorry, this is capital N here, a n is equal to some p pi, and which gives me a is equal to p pi by n, where p is again an integer going from 0, 1, 2 and so on. So, using that, now I have the solution for this equation. That means now we have the basis function phi p n, and the basis function in our case is this. Now, the only issue is we do not know what alpha is. Now, for any value of alpha, we will have a linear transformation. So, it is up to us which alpha value we are going to choose. So, we will choose alpha equal to 1 by n, that is phi p n will be 1 by n cos p pi n by n, and the reason why we have taken alpha is equal to 1 by n is because if you recall, my x p is given by this, dn is of the order of n. So, if I multiply this with a quantity that is of the order of 1 by n, the net quantity will be of the order of unity. That is one justification why we are taking alpha equal to 1 by n, because that gives me a quantity of the order of unity in the equation I have written for x p. So, just to conclude, so we have now obtained the basis function phi p n. Using that, now I can get the solutions x p, which will then be used to solve the ordinary differential equations that I have written, the star here, and by solution of those equations we can get the solution of the Rouse model. So, we continue from this point in the next lecture. Thank you.